はい、始めました。
はい。画面の共有って許可していただいてますよね、皆さんね。はい。わかりました。英語の方がいいですよね。ちょっとまだ入られてる方がいるので、少し1、2分待ちましょうか。So please wait 1 minute, 1 or 2 minutes, because some people try to join the meeting. So please wait a few minutes. いいですかね。では、始めようと思います。So, thank you for attending Typhoon Seminar 2021. I'm Kosuke Ito, working at the University of Syracuse. This year, we are glad to invite Professor Johnny Chan as our distinguished lecturer for this seminar. And let me first introduce what is a Typhoon seminar, and also let me briefly introduce Professor Johnny Chan. So I'm sorry to prepare this presentation in Japanese because most of the participants are Japanese. Typhoon seminar is try to understand the tropical cyclone dynamics from various aspects. And each year, lecturer will have a 3 or 6 hours lecture. And the first time was held 2011, and this time is the 11th Typhoon seminar. And this event was hosted by Nagoya University IC, and also co-hosted by Typhoon Research Group of Meteorological Society of Japan. And I have a list of the lecturers in this 11th year, and a lot of topics were given in the previous years. And this year, we are happy to invite Professor Johnny Chan today. And those who attend this Typhoon seminar for the first time, I'd like to say one thing. All previous lecture notes or videos were already uploaded in the website of Meteorological Society Japan Typhoon Research Group website. So if you want to learn tropical cyclone dynamics, you can visit the website of this page. Okay, so let me briefly introduce Professor Johnny Chan. He's a professor at the School of Energy and Environment, City University of Hong Kong. And he got the bachelor's degree and master's degree, University of Hong Kong. And he received the PhD degree from the Colorado State University. I'm not sure when, but I heard from Johnny, he said, he first learned something from the Professor Tsutomu Takahashi in Hawaii. So maybe I feel like, he's a close relationship to Japanese scientists since then. And he started his teaching career in 1989 at the City University of Hong Kong. And he is, of course, famous about tropical cyclone track researches, and also genesis works and many other kinds of works. Okay, so the schedule today and tomorrow, we have 3-hour lectures in each day. And we also have a 30 minutes break. I'm sorry, I put the Japanese time. So 1 hour difference from Hong Kong and Japan. So here I start this lecture, and Johnny, maybe you can decide when it's appropriate to have a break. And then today, 6 p.m., we will have an online dinner. Please serve your food in front of you. And as I send you an email, we use the Gather Town to meet in person to eat, online dinner. Okay, so I'm not sure, how much our time is used for each topic, but maybe I just want to encourage, especially students, to ask many questions because, this time is very, very rare and special opportunity for you to ask distinguished Professor Johnny Cham. And if you are not good at speaking English, maybe you can put your questions to chat. Even if you don't want to show your names, but just you can privately send me chat and in Japanese. I will translate and I will ask Johnny in English. Okay, so just let me briefly summarize my talk in Japanese. Is it okay, Johnny?
Sure.
今冒頭でお話しした通りなんですけれども、ぜひ最後にもお話ししましたように、学生さんにぜひとも積極的に質問していただければというふうに、学生さんとかですね、若い皆さん、あとは研究者の皆さんに質問していただければと思います。で、英語で質問するのがちょっと辛いなと思う場合にはですね、ぜひチャットで日本語で伊藤宛てでも構いませんので、質問を送ってください。ちょっとこれは当たり前だろうと思うような質問でも全然受け付けますので、ぜひそこら辺の積極的に質問していただいて議論を盛り上げていただければと思います。Okay, I'm sorry to talk something in Japanese. Okay, now it's time to give you the time, Johnny. So please start your presentation now.
Okay. So good afternoon. My colleagues from Japan and also maybe other who have joined the seminar. Ito-san mentioned about my connection with the Japanese scientists many years ago, and yes, it was true that when I started doing a PhD in the University of Hawaii. Some of you might not know about this, so I'll give you a bit of that. I started doing my PhD in the University of Hawaii under Professor Takahashi, Tsutomu Takahashi, and some of you might know who he's a world famous expert in cloud physics. And so I started learning cloud physics from him in University of Hawaii. But after a while, I thought, well, cloud physics was very theoretical. Not much practical use. So then that's when I switched to Colorado State and study under Professor William Gray, and that kind of switched my study from cloud physics to tropical cyclones. And of course, since then I've been in contact with many Japanese scientists throughout the years, and so hopefully. This set of lectures will give you some idea about what tropical cyclone motion is all about. So let me just start share the screen first. Okay. So can you see my screen?
Yes.
Okay. So let me put it. So you can see it now, right?
Yes, yes.
Okay, good. So there will actually be 4 lectures, and what Ito-san mentioned about the first topic will be the main idea of this series of lectures. And so the first lecture will be what I call the fundamental concepts of tropical cyclone motion. And that will probably take about an hour and a half to maybe about 2 hours. and then it's depending on how far along we are, and then we can take a break somewhere. And then we'll have a second topic on the application of this concept. And then tomorrow, I probably will try to finish this 2 topics today. And then tomorrow, we will go to further applications of the tropical cyclone motion. And then I want to spend a bit of time in the second topic, which is on tropical cyclone forecast errors, because that's related to the track forecast. Okay. All right. So and as Ito-san mentioned, that please feel free to ask questions as I go along, and so you can type it in the chat box, or you can actually interrupt me with your microphone. I don't know which one is better, but probably either one is fine with me. I always tell my students that if they have questions, just ask rather than wait till the end of the lecture, because you might forget already. Okay, so basically that's how I will run the lecture. Okay, so the outline of this first lecture is that I will start out with what I call the biotropic concepts, and then which includes the steering and the beta effect, which some of you might have heard of. And then the second part is on the baroclinic processes in the concept of tropical cyclone motion. So steering flow. Now we all know, let me see if I can get the, so you can see my pointer now, right? So if you have a vortex like this, and then there's a flow from the surroundings, and that's what people have called this the steering flow. So it seems very straightforward. However, the question is, where is the steering flow within the tropical cyclone vortex, right? So when we say where, we can ask the question, at what level? Are we looking at a single level, or are we looking at a layer, okay? And then not only do you have the vertical, but also in the horizontal, within what radii from the TC center. All right, so even though we think that the tropical cyclone is moving with the steering flow, we need to ask these 2 questions. So I will start out with the some observational studies, try to answer these 2 questions. Okay, so way back in 1976, when most of you were not born, George and Gray actually did a study using the radiosonde data and looking at the azimuthal average flow at different radii, parallel and relative to the TC motion. Okay, so what it means in here is that when this is vertical, the pressure in millibars, and this is rear and forward, which means that if it's positive in here, that means the tropical cyclone is moving faster than the average flow. So these numbers, 2, 4, 6, 8, 10, and so on, indicates the azimuthally average radius. Okay, so this is 2-degree radius, 4 degrees, 6-degree radius. So obviously, you know that one degree is about 111 kilometers, right? So that's about 200 kilometers, 400, and so on. Right, so this is for a composite of all tropical cyclones in the Western North Pacific at latitudes greater than 20 degrees, okay? Now, for those that are in the southern part, that's latitude less than 20 degrees, you have the similar variation in the vertical, okay? So what you see here is that there are some, close to the center, it seems that this tropical cyclone is moving slower, and then the flow within near the center, but then outside here, it seems that the tropical cyclone is moving faster than this average flow. Okay, so furthermore, you can see that if you look at, because this is relative to TC motion, so if you want to look at the steering flow, you might want to look at what is closest to 0, so that it is it will be the same as the motion of the tropical cyclone. So what you see here is roughly in the middle troposphere, from about 850 hectopascal to about 300, then and then within about maybe 4 or 6 degrees and so, that's where you have the closest to the tropical cyclone motion. Now here, now the other thing that's important is that the variation in the vertical is also very small within this layer, okay? In the upper troposphere or in the lower troposphere, the variation is a lot more, but in the middle troposphere, the variation is a bit less. So you can see, for example, in the southern part, then the closest will again be about 4 to 6 degrees. Now, so this is the parallel condition, right? So what about the normal to the TC motion? Normal means that you will see whether the steering flow is parallel to the tropical cyclone motion, or is that at an angle to the tropical cyclone motion? And again, if you look at latitude of greater than 20 degrees, that means that, so you can see in most cases, the flow is actually to the right of the TC motion. And similarly, in the latitude, that the flow is to the right of the motion. That means that the TC is moving to the left of the steering flow. Okay, so again, you can see in the middle, but there, in most cases, it's larger. So there's no case in which it is actually perpendicular. So it's actually always to the right of TC motion, and for higher latitudes, the angle seems to the magnitude seems to be bigger, and for lower latitudes, the magnitude seems to be smaller. And again, you can see that in the middle troposphere, the variation is the least. Okay, so this is the first thing that you can see from an observational study from George and Gray. Now, later on, I did a study in 1982, again with Professor Gray, and then we split a bit more into different categories. So you can see this is compositing latitude, speed, direction, and intensity. And we specifically look at 5 to 7 degrees latitude, because if you recall from here, that most of the variation, the one that's closest is within this range, about 5 to 7. So we specifically look at 5 to 7 degrees, and this is the directional deviation from the tropical cyclone motion vector. Now, directional deviation means that, again, it will be normal to the storm, okay? So when it's normal to the storm, you see here is that in all the cases, irrespective of whether it's latitude, speed, direction, intensity, and if you look at the mid-troposphere, the variation is the smallest, but they're all positive. Positive means, again, that the tropical cyclone is moving to the left of the steering flow, okay? To the left of the steering flow. And similarly for the category of intensity change, size and intensity, so you can see deepening, filling, small, and tropical storm, and small typhoon, medium typhoon, large typhoon, and so on. So all these angles, all these deviations are positive. So again, whatever you do, whatever characteristic of the tropical cyclone you have, the tropical cyclone is almost always moving to the left of the average flow within 5 to 7 degrees. Okay. Now for the speed deviation, so this is the speed now. So for the speed, the magnitude, it's a bit small. So usually it's about 1 to 2 meters per second, and there's a bit of a variation. Although within this 850 to 300, the variation is the smallest. But in some cases, for example, here south of 20 degrees, the speed deviation is negative. Okay, and in some cases it's a bit positive, and so on. So it's not as clear as that of the directional deviation, but in most cases, the deviation is negative. That means that the tropical cyclone is moving faster than the steering flow. Okay, so similarly here, you can see that in most cases it's negative. So that means the tropical cyclone is moving faster than that of the steering flow. Okay, now the other thing that you can also, we say that you have 850 to 300 being the kind of like the optimal layer. Now, however, there was a study by Chris Veldon and Lance Leslie in 1991. And for different tropical cyclone intensity, the optimal steering flow layer that they found in the Australian region is different. So for weaker tropical cyclones, right, that the optimal steering layer is actually between 850 and 500. However, if you go to the more intense tropical cyclones with the mean sea level pressure of less than 945 hectopascals, so you see that the optimal layer is actually much higher. So this is an important finding, is that on the average, you can say that in, the steering layer is maybe within 850 to 300, okay? However, for weaker storms, you might want to actually look at the shallower layer, and for more intense storms, you want to look at it at a much deeper layer. So that's very important, and we'll come back to this later on when we talk about tropical cyclone forecast in tomorrow's lecture. Okay. So based on these observations, we can give some answers to the two questions that I posed in the beginning. So at what level or within which layer? So the answer from the observational studies is that the best relations with tropical cyclones appears to be in the mid-troposphere or average within the main part of the troposphere, okay? However, it might also depend on tropical cyclone intensity with a deeper layer for a more intense tropical cyclone, all right? So the second question is within what radii from the TC center? So the relationship, the best relationship seems to be within 5 to 7 degrees latitude radial band. And it's quite intuitively obvious because you want to reduce the impact of the tropical cyclone circulation, because if you're too close to the center, then you will have you will include a lot of the tropical cyclone circulation. But if you go too far away, then the flow might not be related to the movement of the tropical cyclone. So therefore, it seems that the 5 to 7 degree latitude is probably the optimal radii you want to use, okay? Now, however, the results from we also have two important very important results in this from the observational studies, is that irrespective of how the steering flow is defined, a tropical cyclone tends to move to the left in the northern hemisphere. And in fact, I haven't shown this, but you can actually do the same thing. But if you look at those storms in the southern hemisphere, it will be actually to the right of the steering flow. So immediately from this observation, you can think about this maybe as related to the Coriolis effect, which we'll talk about later on. And the other very important part is that with a speed larger than that of the steering flow, okay, so the steering flow, doesn't matter how you define it. In generally speaking, the tropical cyclone does not move with the steering flow. So it will, in most cases, it will move to the left of the steering flow and faster than the steering flow. So these are the two very important results that came out with the observational studies, okay? Okay, now, even though I started showing the results from George and Gray in 1976, but in fact, many years before then, Herbert Real in 1954, in his book on in tropical meteorology, has already said something very similar. So he said in the book, in fact, he was summarizing results of even results from studies before his publication. he said that the tropical cyclones move under the influence of external and internal forces. Okay, so what are the external forces? So external forces are applied by the currents that surround a storm on all sides and carry it along, which is the steering current that I just mentioned to you. Okay, so that's what he referred to as the external forces. He also mentioned something very important, which is the internal force. So he said internal forces arise within the tropical cyclone circulation because of the variation of the Coriolis force across the cyclone. Okay, and in fact, that was first proposed by Rossby in 1948. But I don't want to go too far back into the history. But I just want to point out that the observation that the tropical cyclone moves generally with the steering flow, but there's also this internal force, has been recognized for many years, for almost close to a century. Okay, so what he said was that in the mean, tropical storms move in the direction and with the speed of the steering current. So that's what he said, in the mean, defined as the pressure-weighted mean flow from the surface to 300 millibars over a band of 8-degree latitude from the cyclone center. So this result that he mentioned in 1954 was actually quite similar. Now, obviously, you know that in 1954, or even before then, there were very few observations, very few radiosonde observations. And so he was able to conclude from the studies that he did and many of the previous researchers that the pressure of weighted mean flow from surface to 300, so that's very similar to what we said about 850 to 300, and over a band of 8-degree latitude. So we said 5 to 7 is the optimal. So that's very close to what we said in the observational studies. Now, very importantly, also is that the internal forces cannot produce displacements averaging more than 1 to 2 knots. Okay, so that's what he said. And he said the reason for, if the internal forces were very large, then you would see very large deviations of the tropical cyclone motion from the steering current, right? But in fact, what he studied compared with all the other previous studies also show that in the mean, the tropical cyclones move with the steering flow, and there's a bit of a deviation, but not very large. Right. So these are the two concepts that I like you to remember right now, and then we'll try to understand why this is the case. Okay. So this is a bit of the historical perspective. So in fact, if you this is another study by Carl and Ellsbury later on, summarizing all the observational studies for both the Western North Pacific and the Australian region. And so what this is plotting is the tropical cyclone motion vector minus the 5 to 7 degrees azimuthally average flow vector. What it means is that if you have, so this is the difference between the two vectors. So these rings are the magnitudes. So they're all positive. That means the tropical cyclone motion is always larger than this flow vector because they're all, and the magnitude is about 1 to 2 meters per second, right? So generally speaking, roughly about 1 to 2 meters per second. And the direction is very interesting. You can see that the direction here, so this is for latitude. So it's latitude less than 20 degrees, greater than 20 degrees. So moving direction means that these are the eastward moving storms, northward moving storms, westward moving storms. So these are the fast moving, slow moving, medium speed. Intensity is weak, intense, and very intense. And in the Australia region, similarly, this is the direction, and also recurvature, that's before recurvature, after recurvature, and no recurvature. So, but what's important in these results is that in the northern hemisphere, in these four charts in here, that all these vectors are pointing towards the northwest, except for this one. Okay, so what does that mean? So you can see that all these are pointing towards the northwest, west northwest. So that means if you take the difference between those two vectors, the difference is always a positive magnitude, and the direction is always pointing towards the northwest. Okay, So that's what we see. In the southern hemisphere, in most cases, again, the magnitude is positive, but the angle is pointing towards the southwest. Okay, so one is that the magnitude is always positive, and two is that the deviation is always pointing towards the west and towards the pole. So in the northern hemisphere, it's towards the northwest, and the southern hemisphere is pointing towards the southwest. So it's westward and poleward, right? Westward and poleward, very important. Okay. So now let's try to understand a bit more from the dynamic perspective by looking at the vorticity equation. Okay, so we all know about the vorticity equation, so I don't need to spend more time on it. So this is the horizontal advection term, vertical advection term, the divergence term, and the tilting term, right? So these are the usual definition of the terms. So now, if you look at the local change of vorticity, so LC is this term here, all right? The local change in relative vorticity. So this is one example at 2 degree latitude radius. Okay, so we want to look at the motion itself and how that is being driven by the different terms. So here is so how do you look at this? So basically, you have a tropical cyclone like this, right? So what you do is you open it up. So instead of cylinder like this, you open it up so that here you have the front 0 degrees, 90 degrees, and then this part is, so this is the azimuth. So this is the front part, and this is the back part, okay? Right, so, and this is the vertical. This is one example of the fast-moving storms. Right? So what you see in here is that in the front, the local change is positive. Okay? Local change is positive in the front and negative in the back. So which means that the vorticity, as the tropical cyclone moves along, the relative vorticity increases in the front and decreases in the back, right? So what you see is a maximum in the front and minimum in the rear. Now, what does that mean? It means that it's an increase in relative vorticity, therefore obviously implies a spin up of the air because now you have an increase in the vorticity. So therefore air spins up. And so through geostrophic adjustment, so when you have a spin up like this, so obviously with the geostrophic adjustment, then it will lead to a lowering of the surface pressure, right? And so you can therefore interpret that from a dynamical perspective, that the tropical cyclone movement can be viewed as a continuous increase in relative vorticity in front of the tropical cyclone. So the movement of a tropical cyclone from a vorticity perspective is that there is a continuous increase in the relative vorticity in front of the tropical cyclone. And through geostrophic adjustment, then the vortex looks like it's moving continuously towards the front, right? So that was one example in here for the fast-moving storms. But we also looked at the turning storms. So if you look at composites of storms making a left turn versus those going straight and those making a right turn, that means recurvature. And you look at the local change in relative vorticity. So what you see here, so the red dot is the tropical cyclone center. So this is the change in the vorticity between the time of turn. So this is T, that's the time of turn, minus 12 hours ago. So this is the difference. So when you calculate the local change, then you look at the vorticity here minus the vorticity at this time. So what you see is that the change is for left turning storms, the maximum change is to the left of the tropical cyclone center, the straight moving ones is just ahead of the tropical cyclone center. And then for the right turning storms is actually to the right of the tropical cyclone center. So in other words, what you see here is that you will have the tropical cyclones turning into the area where you have the maximum change in the relative vorticity. All right. So again, not only do you look at storms that are continuously moving straight, but if you look at those that turn left or turn right, you still see that the largest increase in relative vorticity is to the direction towards which the tropical cyclone will move, right? So that again demonstrates that the local change in relative vorticity is important in terms of understanding why tropical cyclones move. Now, so the question is, which term is more important, right? Recall we're saying that you have different terms in the vorticity equation. So you have the horizontal advection, vertical advection, the divergence term, and the tilting term. So they are the four terms in the vorticity equation. And R is the sum of these four terms, okay? And then the LC is given by calculating the vorticity change in two different time periods, right? Plus this time minus 12 hours ago. So I'll show an example of slow moving storms versus fast moving storms. And so this is the variation in the vertical. So what you see here is that the variation is the smallest for this term, the horizontal advection. Now the local change is also about there's not much change in the vertical like this between 850 and about 300. So that's about constant in the vertical. So if you look at the various terms, first of all, the tilting term given by the purple line is very small, right? So you can kind of ignore that. The contribution of the tilting term is very small. The divergence term is also very small in the mid-troposphere. It's very large in the below 900 millibars or above 300. Okay, similarly here, above 300 or below 900. And that's obviously because in these two layers, so you have a very strong convergence in here and very large divergence in here. And that's what's contributing towards the change in here. So these two terms, the tilting term can be ignored. Divergence term is only important in the upper in the upper troposphere and within the boundary layer. So we can also ignore that. For the vertical variation, vertical advection, sorry, it's also relatively small in the mid-troposphere, and there's a bit larger in here, obviously, because the vertical advection is related to the vertical motion, which is related to the divergence and convergence, right? So therefore, in the lower and upper troposphere, they are larger, but in the mid-troposphere is very small. So what is left? What is left is the HA term, the horizontal advection term. The horizontal advection term is given by the blue line, and you can see that the blue line has very little variation in the vertical. And very importantly is that the the HA term, it's very similar to the green line, which is the local change, all right? And of course, if you sum all the four terms R, it's also very similar to the HA term in the mid-troposphere, because these other terms are relatively small in the mid-troposphere, okay? So what you see here is therefore the vertical advection.
Excuse me.
Yes.
May I ask you a question?
Sure.
In the previous slide, let me confirm that the contributions of diabetic heating and friction are small compared to distance.
Very good question. First of all, this is the vorticity equation. So therefore, there's no diabetic heating in the equation. And for the friction, it is not shown in here, but you can also see that if you add the four terms, then it's not the same as that LC, and the difference is because of the friction. So you can see that the difference is mainly in the friction term. But in the mid-troposphere, because there's not much friction, so therefore these two are very similar. So we did not calculate the friction term, and so whatever the difference between the LC and the R, you can infer that to be the frictional term.
Okay, thank you.
Okay, all right. So because there's no, I'll come back to diabetic heating later on when we talk about the baroclinic processes. All right. Okay.
Thank you.
So vertical advection and tilting terms are small. Now the divergence term is only significant in the lower and upper troposphere. And so therefore the local change of vorticity is mainly contributed by the horizontal advection term, especially in the mid-troposphere. So very importantly is that integrated over the entire troposphere, the horizontal advection term still dominates. So therefore, to a first approximation, that the local change in the relative vorticity is therefore the advection, horizontal advection of the absolute vorticity. And obviously this is the Biotropic Vorticity Equation. Okay, so in the 1980s, in the 1990s, people were mostly focusing on this concept of the Biotropic Vorticity Equation as the concept to explain tropical cyclone motion. So let's look a little bit more about this equation. So if you split this equation up, so let's assume that we are only looking at the horizontal advection term. Okay, so the local change is therefore approximately equal to the horizontal advection of absolute vorticity, which therefore can be split into two parts: the advection of the relative vorticity and also the beta times the meridional flow. So this is obviously this is what we refer to as the steering flow, and this is the beta effect. Okay, so now what we'll come back to this in a minute, but let's finish off with the steering flow concept first. So therefore, the steering flow is, from a dynamical point of view, is that you have the increase in the vorticity due to horizontal advection in the front, and the negative vorticity advection in the back, because you can see, of course, that the gradient of the vorticity, you have the highest vorticity here in the front, so therefore the gradient with the negative sign give you a positive value here, and then here you have a negative value. So therefore, the steering flow is basically the advection of relative vorticity, right? So that's the steering flow concept. Dynamically, it means that the reason why steering flow can push the tropical cyclone forward is because it is advecting relative vorticity to the front of the vortex, which then increases the relative vorticity through adjustment. Therefore, the tropical cyclone moves forward, right? So that's the steering flow concept. Okay, so let me pause for 1 second and see if anybody wants to ask question about the concept of steering flow.
Okay, I have a question.
Yeah.
So steering flow is, kind of a large scale wind flow,
yes,
or not? Just maybe later on you will explain a beta gyre effect. But
this is mostly looking at the environmental flow. Okay, so you can imagine that this is the environmental flow, but of course, again, if you want to estimate the steering flow, the best obviously is outside the tropical cyclone circulation. But of course, within the tropical cyclone circulation, there's also the steering flow, but it's very difficult to estimate that, right? So therefore, there are two things you need to think about. One is, how do we estimate the steering flow? And number two is the dynamical understanding of the steering flow. So when you want to estimate the steering flow from observations or from analysis or whatever, you need to look at further out so that you can eliminate the tropical cyclone circulation. But if you want to look at the concept of the steering flow, it's just basically the advection of the vortex relative vorticity.
Okay, so could you go back to Biotropic Vorticity Equation? Is that one?
Yeah.
Okay, so you mentioned the first term is steering flow and the second term is a beta term, but I guess, nonlinear beta effect can be resulted from the interaction between the steering flow term and the beta effect term.
Yes. Exactly. This is exactly what I want to talk about when we talk about the beta effect. That you need to include a nonlinear term. Yes.
So in that sense, in my mind, I separate the steering flow into the large scale environmental flow and more smaller scale storm scale advection. In that case, I can separate the beta effect and large scale wind. But here, you are mentioning, all advection term can be regarded as a steering flow. So, just I was wondering.
Oh, no. So sorry. So this VH here is basically the environmental flow, because this V is actually the meridional flow. The meridional flow associated with the vortex.
Okay. So
the total flow, obviously, if you look at the total flow, it will be the environmental flow plus the meridional flow. Now, when you talk about nonlinear effect, that's what I'll be talking about in the beta effect, is that you are absolutely correct that you need to include the nonlinear effect. And but here I wrote this like this because that's much easier to separate the understanding of the forcing by the large scale flow versus the forcing by the Coriolis parameter.
Okay. So very clear explanation. Thank you very much.
Yeah. Okay. Right. So let's go to the concept of the beta effect. Okay. Now, and we of course we said this now that the steering flow dominates, so that the tropical cyclone is dominated by the steering flow. Now, what's important is this, that in an environment with a weak flow, then the advection of the planetary vorticity becomes important. And that's what's known as the beta effect. And I'll explain more as we move along. So in the extreme case, if the environmental flow is 0, then the biotropic vorticity equation becomes that the local change equals minus beta V, where beta, of course, is the change of the Coriolis parameter with latitude. Okay, Y is the meridional distance, and V is the meridional wind of the tropical cyclone. And so this is the concept of the beta effect, that the change of the vorticity is given by this term here, which is the change of the Coriolis parameter multiplied by the meridional wind. Now, so this is actually to the west of the tropical cyclone, because if you look at this diagram in here, so what we are showing here is that, so F obvious, so this is in the northern hemisphere, that you have the F increasing with latitude. Okay, so the vortex is moving like this, and the cyclonic circulation is going around like this. So therefore, the tangential wind of the vortex will be advecting higher vorticity to the south on the west side and lower vorticity on the east side. As a result of that, you will have an increase in the vorticity to the west and a decrease in the vorticity in the east. Okay. Now, because of this, again, there's an adjustment between the two, or adjustment to this increase in the vorticity. And so therefore, there is a spin up of the vortex in the front and the decrease in the vorticity in the rear. Okay. So you have a positive, and as a result, you have an increase in the vorticity in the front to the west and a decrease in the vorticity to the east. All right. So this is why you would think that there is a so in other words, you will now have an increase in the vorticity to the west. Now, to explain a bit more, so physically, because beta, if we calculate this on a look at on a beta plane, then beta is constant. So there's a bit of variation across the storm, but it's relatively small. Okay, and the meridional component is maximum to the west of the cyclone. Now, but the important point is this: an increase of vorticity to the west and a decrease of the vorticity to the east, and therefore should induce a secondary circulation, and therefore leads to a northward motion. So the combined effect is therefore should produce a northwestward motion in the southern hemisphere. Then the motion is towards the southwest. Now, but because the Coriolis force is always present, this westward and poleward motion, it should be present in all tropical cyclones, right? So it doesn't matter whether it's intense, not intense, or whatever. Now, so if you now include the steering flow, the movement, and therefore it's the combination of the steering flow and this westward and poleward motion. So I've drawn some examples in here. So the deflection of the beta effect, due to the beta effect, it's always pointing towards the northwest, right? It's given by the green arrow in here. Now, so let's look at the 4 different quadrants with an environmental flow given by V. So if you have a westward steering flow, this is the environmental flow. If you add the beta effect, then the resultant is actually like this, which means that the tropical cyclone is actually moving to the right of the steering flow. However, if the steering flow is towards the northwest, if you add the beta effect, then it's to the left. And similarly here is to the left, and here is to the right. So if you recall that in the, if you look at let me go back to this diagram, and now you can recall this a little bit in here. So if you recall that, for example, in here, that the deviation for the westward moving is a bit different than these two, okay? So the deviation is a bit towards this side. And so it seems that there is a bit of a difference when the storms are moving in different directions. In most cases, they are okay. They are pointing towards the northwest. But in some cases, they may not be. And that's one possible explanation is this one here, that you have, depending on the steering flow, when you add the beta effect, then you have something like this. Now, obviously, this is very simple, okay? So let's not argue whether this is true in the actual observations, because there are many other effects. But let's think about this very simply as a sum of the environmental of the steering flow V plus the beta effect given by the green arrow. All right, so that's what you would expect to see, is that in most cases, because most of the storms are moving towards the northwest and northeast, so if you average all of them, you will see that the angle, the deviation, is actually to the left, and the magnitude of the resulting vector is larger than that of the steering flow. So therefore, what we have found from the observations, that tropical cyclones are moving to the left and faster than the steering flow, could be explained by this one here. So that's why this is the steering flow plus the beta effect. Now, in fact, if you look at observations again, now, these are actual observations from different storms. So these are 1, 2, 3, 4, 7 storms that were examined during a tropical cyclone experiment in 1990. So the dashed line indicates the steering flow, okay? And the solid is the tropical cyclone motion vector. So what you see is that, so for the case of this storm, the tropical cyclone motion is always to the left. And for this storm Ed, there's a bit to the right, but that's because the storm is moving more to the west, and even this part here in the southwest. But all the other cases, they are all moving towards to the left. All right, Winola and Yancy and so on. So these observations, analysis of individual. Now, remember in the early 1980s, we were looking at composites, right? So because at that time there were not enough observations. So for the 1990 experiment, there were a lot more observations, and then we were able to look at the individual case for individual time. All right, so there was also the numerical analysis at the time. So we were able to do this to look at individual cases, and you can see the very similar results, that there's a deviation to the left and faster. Okay, so it seems that the concept of steering flow plus beta effect is quite justified. It seems to be that way. And that's what you see in here, as I showed you before. Okay, so therefore, it seems that the conclusion from both from all these observational studies and a simple mathematical analysis of the different terms in the Biotropic Vorticity Equation is that a tropical cyclone will move in a direction with a speed different from those of the steering flow. And the deviation depends on the direction of the steering flow. Okay? So now, Ito-san mentioned about the linear versus nonlinear beta effect. So that let's go to a bit about that in here. So when we start out with the vorticity equation, if you don't have the feedback process, so if you just integrate the linear vorticity equation with an idealized vorticity, assuming that the changing relative vorticity will not feed back to the meridional wind, then if you solve that equation, okay, you can actually solve that equation analytically because it's linear, so you can solve it analytically. And then what you see is that if you solve the equation, you solve the stream function, which is the Laplacian. The Laplacian of the stream function gives you the vorticity. Okay, so if you start out with a vortex like this, all right. So this is the XY plane. So this is the stream function, and obviously the stream function is more negative. The negative stream function means that you have a positive vorticity. So initially it's like this. In 36 hours, the stream function distribution is like this, and the 72-hour distribution is like this. So what it's showing is that the vortex actually has not moved. So 0 and 0. Let me go back to the laser pointer here. So 0, 0 is the center in the beginning. And after 72 hours, it was still about the same. And the whole vortex is actually stretched towards the west. So there's no movement. So what's going on? So what we see here, instead of a northwestward motion, the vortex remains almost stationary, but is stretched westward, okay? And the westward stretch is actually due to the Rossby wave dispersion, because if you go back to here, that if you decompose this one here, obviously you have different wave numbers. You have high wave numbers here, and low wave numbers here, and high wave numbers up there. So therefore, the longer waves, that means the smaller wave numbers, dispersing faster, so that the outer circulation propagates more and leading to the stretch of the vortex. So therefore, if you just solve the equation without considering the feedback between the vorticity change and the meridional wind itself, then you have this problem. So therefore, the linear beta effect, as what you asked, is that cannot explain the observed beta effect. Okay, so let's understand a bit more from here. So if you solve the equation, but what you do now, if you solve the equation, but now you allow a feedback. So when you have an increase in the vorticity in here, that it fits back to the meridional wind, it fits back to the invection term in here. Okay, so so if you solve it now, you have to solve it numerically, and then you would get something like this. Then in 36 hours, in 72 hours, now the vortex starts from here, and now it migrates towards the northwest. Okay, so so that's the track in 72 hours. If you include the nonlinear beta effect. And in fact, the reason for this is because the vorticity and the stream function propagate differently towards the west. And so as a result, there's a mismatch between the stream function and the vorticity. And of course, the gradient of the stream function gives you the stream flow, the flow itself. And so therefore, you can see that in the middle, you have a strong gradient in here, and therefore that's what's affecting the vorticity forward and causing the tropical cyclone to move towards the northwest. Right, and in fact, that's what you will see, that there is a maximum of wind in the northwest. I'm sorry, northeast of the storm, and that's what pushing the storm towards the northwest. Okay, so to understand a bit more about this, Fiorino and Ellsbury in 1989, 2 years after we published this paper in here, they split up the equation, the invection term. Now here again, there is no environmental flow, so it's just the vortex circulation itself. So they split up the invection into three parts. So here is the asymmetric invection of symmetric vorticity. That means symmetric vorticity means that the azimuthal average vorticity, and the asymmetric invection is the subtraction of the symmetric part. What's left over is the asymmetric part. Right? So then the other part is the symmetric invection of asymmetric vorticity. And the last part, which is relatively small, is the asymmetric invection of asymmetric vorticity. So you can look at these three parts, and this part is actually very small. So let's think about these two here. So let's go back to this diagram in here. The nonlinear beta effect is that if you look at this one here, when you increase, so how do you interpret the two terms? So this term here, when we say in here that there's an increase in the vorticity due to the Coriolis force. So this is the advection of this asymmetric of the symmetric vorticity, because you are affecting it's the advection by the meridional flow of the symmetric vorticity in here. Okay. Now, however, you have the cyclone itself. So this is the symmetric advection of the asymmetric vorticity, which is the F. The asymmetric vorticity is the F. So it's actually, you have this advection in here. So if you add these two together, so what happens is that you have, when you increase the vorticity due to the increase in the vorticity, so this cyclonic circulation and this anticyclonic circulation. So these two cyclonic, one is cyclonic circulation, one is the anticyclonic circulation. Then they're being advected by the vortex itself. So this is the nonlinear part. So not only do you have the change in the vorticity due to the advection of F, you now have the vortex will now be rotating this change in the vorticity. Now, previously, we said in the beginning that the increase in the vorticity here and the decreased vorticity will produce a northward flow. But in fact, it is not true, because as it starts then there's this rotation. So there's this rotation of the two change in the vorticity. So therefore, you will end up with an equilibrium configuration, so that you have a positive, the increase in the vorticity is the maximum like that, and the negative is here. So instead of a east-west change in the vorticity or increase in the vorticity, now you have a southwest northeast orientation. Okay, so this set of asymmetric stream function are what is referred to as the beta gyres. Okay, so now remember, the gradient of the stream function gives you the flow. So therefore, if you have a negative stream function in here, more negative in the center, and here you have a positive stream function and the highest stream positive in here. So therefore, the gradient of the stream function gives you the flow, and so this is what is referred to as the ventilation flow. Okay. So the beta effect, the nonlinear beta effect, therefore, is actually causing the tropical cyclone towards the move towards the northwest, because of the nonlinear beta effect that creates a set of beta gyres, which then leads to a ventilation flow towards the northwest. So the concept, the conclusion then is that a tropical cyclone will move in a direction with a speed different from those of the steering flow due to the nonlinear beta effect. Okay, so now what we have now come to the conclusion as the first part, or looking from the biotropic perspective, is that a tropical cyclone, if you consider that as one column of vortex, a column vortex like this, then the column vortex moves like this for two reasons. One is the steering flow that pushes it forward through the invection of relative vorticity, and at the same time, because of the beta effect, which then generates a set of beta gyres, and therefore the beta gyre will cause the tropical cyclone to deviate from the steering flow, such that it will be moving towards the northwest with a speed that's larger than that of the steering flow. So that's basically the concept of the barotropic concept of tropical cyclone motion. All right, so I'll stop again and see if there are any questions, or if there are some part that you are still not very clear.
というわけで、何か質問がありましたら、ある方はぜひお願いします。もうどんな質問でも結構ですし、気軽に聞いていただければと思います。
No questions?
Okay, so Johnny, so let me ask one question. So could you go back one slide?
Yes.
So my understanding is linear effect is kind of Rossby wave.
Yes.
You said that the Rossby wave contribution is minor in terms of tropical cyclone motion, but do you think is that true for the real tropical cyclone motion? Of course, in this case, in the left-hand side of this figure, the pressure decrease and vorticity increase. So actual TC motion seems to me, is a combination of this kind of storm scale ventilation flow and also the changes of the vorticity field. How do you think about that?
You could say that. It is possible that the Rossby wave, of course, will, I mean, obviously the Rossby wave will have some contribution towards the movement, but then the propagation, because it's largely because the vortex has many wave numbers. So therefore, as the whole vortex propagates, then, so it's not like a Rossby wave in the westerlies, where you have a quite a well-defined wavelength. So because the vortex has many wavelengths, so therefore there is a stretching of the vortex itself. So what I'm saying is that if you just use the Rossby wave, the linear beta effect, you will not be able to explain the propagation entirely. You could explain a little bit of that. I mean, you still have a bit of movement, but the movement is mainly by the outer part of the circulation. So it could explain, I mean, if you think about this, we haven't done this, but you can think about this, whether that will be related to the change in the size of the circulation, that it could, but as far as the motion itself is concerned, I think that will be a minor contribution, I think.
Yeah, thank you very much. Yeah, I agree, but it's very hard to separate these effects. So
yeah.
Okay, so any other question? If you have any question in Japanese, it's okay. Okay, Nino Sensei, please.
Yes,
Thank
please.
you very much. I'm wondering how much the initial distribution of the vorticity in tropical cyclones affect the nonlinear beta effect.
Very good question. So obviously the nonlinear beta effect depends on the tropical cyclone circulation itself, right? So therefore, if you have an asymmetric, distribution of the tangential winds,
Mm-hmm.
then you will have a different beta effect. In fact, I will talk a little bit about that in tomorrow when we talk about the when you have a change in the circulation itself, then it will actually change the movement of the storm. Part of which is because of the beta effect. Yes.
Mm-hmm.
Yeah.
But my question is, even if you have an asymmetric distribution of vorticity, I'm wondering if the radial distribution of the vorticity will affect
yes. It will. In fact, that's my next topic.
Oh, okay. Okay.
Yeah.
Thank you very much.
I will explain a little bit more about how do you, when you have different intensity or different tangential wind distribution, how would that change the beta effect? Yes, that will be the coming up in a few minutes.
Thank you very much.
Okay, any other question? Feel free to ask questions. Okay, so Johnny, you can take a break here, or maybe just you can.
Let me finish the biotropic part first. It's not. We take another 10 to 15 minutes. Okay, so I will stop after we finish the biotropic part.
Okay.
Okay. So Sensei asked the question, and I will now try to address one of the questions. So how does the beta effect vary with intensity and size? And that's what the question was, that when you have a different axisymmetric distribution of tangential winds, how would that change the beta effect? And the second question is, what if, because the beta, the motion is a combination of the beta effect plus the steering flow. So what if the steering flow is not uniform in the horizontal or in the vertical? So what happens? All right, so I want to address these questions now. So actually, if you look, when we did this study, we actually look at many cases. So now you have different, VM is the maximum wind in meters per second. And this is the radius of maximum wind in kilometers. And this is the direction movement. And you see that they're all three something. That means that they are all moving towards the northwest. But there are some differences, right? So what you see here is that as you increase the radius of maximum wind, the angle actually decreases, right? For this, so for the same maximum wind, the angle decreases. Angle decreases means that it actually moves more westward. Okay. Now, what about the different intensity? So that kind of answers your question a little bit. Is that when you have a different intensity, the more intense the tropical cyclone. So let's look at the column 100 kilometers. That when you have a more intense tropical cyclone, the angle becomes larger. That means it's actually moving more towards the north. Okay, so there is a difference in terms of when you have different intensities and different radius of maximum wind. Okay. Also, if you combine the three, so you have, this is you combine the maximum wind here and the different, and what about the speed change? So that this one here is the directional change. So this is the speed change, that if you have a increase in the maximum wind, so this is a maximum wind, for a given radius of maximum wind in here, then this V is actually the ventilation flow. It's actually larger. So so irrespective of what the radius is, there is always an increase in the ventilation flow with maximum wind. Okay. So you can also see that so that kind of answers Sensei's question about the change in the asymmetric distribution of tangential wind and how the beta effect varies. Fiorino and Ellsbury also look at not only so what we did was look at the radius of maximum wind and also the intensity, but they also look at the outer structure of the storm. So they did 3 experiments. You have this is the tangential wind distribution. So you have the maximum wind here and decreasing with radius. So this radius. And so if you have this, so given the same radius of maximum wind, if you have a smaller vortex, so the red is the 50, means that it is a very small vortex versus a big vortex like this line, black line 20. So a bigger vortex, so given the same intensity, a bigger vortex actually moves faster and more towards the west. A smaller vortex will move slower and more towards the north. Okay, so you can actually do some calculations and see and explain this because of the change on the ventilation flow. Okay, so that's how, so actually this is very important in terms of forecasting. So people these days tend to look at just the numerical weather prediction products. But if the products are wrong in terms of forecasting the intensity and the size, then you can actually lead to a different, it can actually lead to a wrong forecast. Okay, so this is important that people need to think about how the numerical models predict the intensity and the size of the tropical cyclone, because that actually affects the magnitude of the beta effect, which is always present. Even later on when we talk about the baroclinic process, this beta effect will always be there. So that's important. All right, so let's talk a little bit more about the beta effect. Now, if we include the environmental flow now, remember we said before that there was no environmental flow, it's just a pure beta effect. But I won't go into the details of that to understand what's going on, but it's basically just changing the vorticity distribution and therefore changing the what I call the effective beta effect. Because when you, for example, when you have anticyclonic flow, so here are 3 experiments. One is with no flow, that's moving towards the northwest. For cyclonic flow, it's the green, it's about the same, but in the anticyclonic flow, it's still moving towards the northwest, but it's moving much faster. And the reason is because it actually changes the gradient, changes the gradient of the vorticity, right? Because when you have the cyclonic versus the anticyclonic, it changes this. And more importantly, is that if you have a meridional vorticity gradient, now, and this is important because the F is actually the vorticity gradient, right? So if your environmental flow has a vorticity gradient in the north-south direction, then the effective beta changes. So if you are in a cyclonic flow or in an anticyclonic flow, then you will have a different vorticity. So these are the 2 examples in here. 3 examples. This one here is the control. So this is 0, 0. So the control experiment is like this, where it's F plane, meridian. So you have 3 experiments. The red is what we have seen before. It's no flow plus the beta effect. All right, so this is the red. Now, if you have an F plane, so there's no beta, but now if you add the meridional vorticity gradient, which is the same as that is beta, you have a bit different result, right? But very interestingly, if you have a negative beta, then it actually moves in that direction. Okay, so you can actually explain all this very simply by solving the Biotropic Vorticity Equation, and you will find that it's a very interesting result. Similarly, if you now include both the beta and the meridional vorticity gradient, then you will get very different results. So this is the original no flow beta plane. Now, if you increase the meridional vorticity gradient, then that means you double the beta. Then you have a more westward movement. But if you have a gradient that's equal to negative beta, then it's actually moving towards the north. So, I mean, if you're interested, you can go to this paper and have a detailed understanding of what's going on. But the important point, the main point here is that when you think about the movement of a tropical cyclone, you should think about, when you think about the steering flow, it's not just very simple, a uniform flow like this, right? If you have a flow that has a meridional gradient, that it will either increases the beta effect or decreases the beta effects depending on the meridional vorticity gradient. So an example would be if you have a very strong anticyclone to the north and very strong cyclonic flow to the south, let's say in the monsoon trough, then your meridional gradient changes, right? Or if you have a jet, if you have a jet, then there is a meridional vorticity gradient. So if the tropical cyclone is in the jet or moving into a jet, then the meridional vorticity gradient changes, and so there's an additional term that will cause a modification of the beta effect. right? So that's important to think about when looking at the actual storm motion. So what I would call this as the generalized beta effect is the beta effect itself plus the meridional vorticity gradient of the environmental flow. Okay, so I think I'll stop here for the biotropic part. So let's see if there are any questions. If not, then we'll have a break.
Okay, thank you very much. Any question or comments? So Johnny, could you add some more explanation on the size impact on the TC track? What mechanism can explain the larger tropical cyclone goes more westward?
Okay, it's because if you, according to, I mean, this is a study by Fiorino and Ellsbury, and their explanation is that when you have a bigger cyclone, what happens is that it actually generates a much stronger beta gyres, and also because the outer circulation is very large, so the rotation of the beta gyres becomes more compared with a very small cyclone that only rotates part of the beta gyre, and therefore it moves more towards the north. So it's the outer circulation. So the reason why they think it's important is the outer circulation is what's driving the change in the magnitude of the beta effect. So it's the magnitude of the beta gyre itself plus the rotation, as I said, about the symmetric advection of this asymmetric vorticity is what's driving the ventilation flow.
Yeah, just I'm interested in why the direction changes, because larger vorticity requires more large changes, right?
Yeah, but I think it's because they rotate much more. Because the entire beta gyre it's stronger, and also it's because it extends further out, then it rotates a lot more. I mean, you can go back to their paper and see a little bit more.
Okay, thank you very much. Any other question? Okay, so if you have any question, you can use a chat, or maybe you can ask questions after the break. Okay, so now we have a 30 minutes break, and we will resume the lecture from 4 o'clock. Is it okay, Johnny?
Yes. Okay.
So please take a.
Okay, I'll see you a bit. Yeah. Okay.
Thank you. Okay, so it's time to resume the lecture. We have several announcements. First one is some corrections were applied in a second PDF file. So please take your revised version of PDF file in the chat. And also second is I think Nino Sensei have some comments on the previous lecture. Could you explain, Nino Sensei?
I think if you read the comments, that's enough, I think. Yeah.
Okay.
I think it's an interesting comment. I haven't thought of it in that from that perspective, but I will go back and think a little bit more. I think that's interesting.
Thank you.
Yeah.
Okay, so Johnny, please go ahead your talk.
Okay. Okay. So the second part of this fundamental concept lecture is to extend beyond the biotropic concept, because in the biotropic concept, we think of the vortex as a column vortex, right? So, kind of like a one-layer fluid. So, however, of course, that in the real atmosphere, it's not one-layer fluid. So therefore, we need to think about the baroclinic processes. And if you think about the history, it's like this: in the early 80s and so on, people were not really sure about the concept, the entire theoretical framework, and also because the computer power at that time was very weak. So that's why people have been looking at it from the biotropic perspective. However, then starting from the 1990s, people start thinking about, well, we now know what's going on as a one-layer fluid. So what about in the real atmosphere? Or how does that compare? How do the biotropic results compare with the actual observations in the real atmosphere? So the basic starting point is this about the beta effect. We all know about the beta effect just now. So what's shown in here is the beta gyres. Now in the lower atmosphere, you have the beta gyres, but also in the upper atmosphere, you also have this. However, as we all know, that as you move up into the troposphere, the vortex size decreases, and the circulation decreases. So therefore, Ellsbury proposed that because of this, then the extent of the beta gyres will also become different. So it's saying that because the cyclone weakens as you go up into the upper troposphere, so therefore the beta gyre also becomes smaller. And so therefore, if you have so it's the same thing that if you have a ventilation flow in the lower troposphere like this, but in the upper troposphere, the ventilation flow becomes weaker, then you will now have a secondary circulation like this, right? So where you have a change in the beta effect. So the question is, how does this beta effect then, how does this, what we call the differential beta effect, affect the movement of the tropical cyclone? So I will now just use this approach that has been quite accepted now in the tropical cyclone community to study tropical cyclone motion when you're thinking about the three-dimensional atmosphere instead of a two-dimensional. So this is the Wu and Wang's approach on potential vorticity. So his proposal, or their proposal, is that the tropical cyclone will move towards an area of maximum potential vorticity tendency. Okay, so what does that mean? Now, first of all, let's look at the equation of the potential vorticity. So P is the potential vorticity, and the subscript 1 means that it is the wave, azimuthal wave number 1. So what you do is you have this tropical cyclone circulation, and if you do a Fourier decomposition around the azimuth, and then you only pick the wave number 1 out from the decomposition. And so the wave number 1 change in the potential vorticity with time, so this is partial P1, partial T, is then, so lambda 1 is the wave number 1 operator, will be the wave number 1 of these 4 terms. So you have, if you look at the potential vorticity equation, it will be the horizontal advection, vertical advection, diabetic heating, plus the friction. Okay, so what they propose is that for the friction, it's important only in the planetary boundary layer, right? So if you again ignore what's happening in the PBL, then you can kind of ignore the contribution from friction. The vertical advection, as I showed you before, is important, of course, near the eye and in the tropopause. But other than that, the vertical advection may not be very important. So therefore, what you see is that the main contribution of the potential vorticity is due to the horizontal advection and diabetic heating term, which I'll explain a bit more as we move on. So what they did then is that they calculate, or this is a numerical result. So they ran a model and then look at the contribution of each of these terms and represent that as a vector. So C is that the solution in the model of the motion of the tropical cyclone. Okay, so they look at 3 levels. So you have level at 850, 730, and 580 millibars. So again, what you see here in the mid-troposphere, the vertical advection is relatively small. So you can kind of ignore that. So the combination, the motion of a tropical cyclone then is a vector sum of the horizontal advection and the HE, which is diabetic heating term. Okay, so but very important note that because in the vertical, the steering flow might change. So horizontal advection, you might think of it as the steering flow, but it's a bit more complicated than that. I'll explain a bit more about that in a minute. So the horizontal advection also changes in the vertical. So for example, it points towards like this, and as you go higher up, the horizontal advection changes. The heating also changes, but mostly in the magnitude, but not much in that direction, in terms of direction. So if you sum up these 2 vectors, you can basically explain that of the cyclone motion. So that's basically the concept that's proposed by Wu and Wang based on numerical simulations. Now let's look at a little bit more about this horizontal advection, which I think is important to understand. So the horizontal advection term, again, the wave number 1, can then be separated into 2 components, right? So you can actually break that up in the V1 is the advection of the potential vorticity, symmetric potential vorticity. So S represents symmetric. So this term is the advection of the symmetric potential vorticity by the asymmetric flow. Then the second term is the advection of the asymmetric potential vorticity by the symmetric flow. Okay, and so of course you can have a third term which is very small. It's the advection of the asymmetric potential vorticity by the asymmetric flow. Now, so if you look at these 2, what is contributing towards each of these 2 terms? Now, the asymmetric flow, of course, it can be the steering flow or the environmental flow. It can also be the ventilation flow due to the beta effect. So this is asymmetric. Or, very importantly, there is a flow associated with the asymmetric convection, okay? Because we're now thinking about 3-dimensional, so there could be asymmetric convection. Now, because it's the advection of symmetric PV, so symmetric PV, of course, the most important part is the vortex potential vorticity. But there is also the symmetric part of the environmental flow. So for example, if you have a cyclonic, if you are in the monsoon trough, you have actually a cyclonic shear, so you have an increase in the potential vorticity, or any potential vorticity associated with symmetric convection, right? Then the other component of the horizontal advection is the vortex flow. The symmetric flow, of course, is the mostly importantly is the vortex itself, or the symmetric part of the environmental flow. But then for the asymmetric potential vorticity can be associated with beta gyres. Remember, we say that the beta gyre can be rotated by the symmetric advection. The potential vorticity associated with the asymmetric convection and then the potential vorticity associated with the asymmetric component of the environmental flow. So therefore, in the three-dimensional world, the horizontal advection of potential vorticity can be quite complicated. All right. So, and what about the diabetic heating term? Now, if you write that in, you can actually write the diabetic heating as a sum of three terms. So you have the absolute vorticity multiplied by the vertical gradient of heating. And the other two terms is the vertical shear multiplied by the horizontal gradient of heating. Okay. So in some sense, if you compare that with the vorticity equation itself, so the Biotropic, if you think about the vorticity equation, this term, the first term, is kind of like the divergence term. These two terms are actually similar to that of the tilting term, because you can, so the tilting term has the shear itself plus the gradient of the vertical motion, right? So the tilting term is that you have the shear that's being tilted by the horizontal wind. So here it is the shear that's modified by the gradient of the heating. So in some sense, in the potential vorticity perspective, you can think of, if you go back to the vorticity perspective, then you can think of these two terms as the tilting term. Okay. Right. So in the simple explanation, then the change in the potential vorticity with time then can be the sum of the three terms: the symmetric advection of symmetric PV plus the symmetric advection of asymmetric PV plus the heating itself. And also remember that this is the wave number one heating. Okay. All right. Now, also very importantly, it is not the heating itself. So it's not Q. It's the gradient of Q. Okay. So it's the gradient in the vertical and also the gradient in the horizontal. So it's important to think it's not just how much heating there is, but what is the gradient of the heating, both in the horizontal and in the vertical. Okay. Right. So let's look at a few examples of this calculating the PV to understand whether this is possible. So Wu and Wang proposed this theoretical framework, and so we did a study later on using this framework to see whether his theory can be verified from observations. So let's look at a couple of examples. So this is a storm, and what's plotted here is the potential vorticity on the 350K PV surface. And so let's say the storm is moving in this direction. So if you think of it this way, then of course there's a steering flow pushing the storm moving this way. So if you calculate the different terms, so this is the asymmetric advection of symmetric PV. This is the symmetric advection of asymmetric PV. So shaded means positive. So what you see here, and the blue line is the advection. So the black line is the advection. Sorry, the black line is the steering, and the blue line is the motion. Okay, so in this case, you can see the steering basically dominates because the symmetric advection of asymmetric PV is actually in having a positive in this direction. Also, you can see in here that the magnitude is only 0.7 units compared with about 5.4 units in here for the steering. So in this case, the advection is dominated by the steering itself. All right, so the motion of the storm. So this is the total PV advection, which is almost exactly the same as that of the tropical cyclone motion. right? So that's no different from the case of steering. So that's easy to understand. Now, so what we did then is to look at 31 tropical cyclones with a total number of cases of 310. And so we classified into 3 groups. One is that the tropical cyclone moves towards the steering vector. And the criteria is that the deviation between the steering vector and the motion vector is less than 10 degrees. Another group is the TC moving towards the diabetic heating vector, and the deviation is less than 15 degrees. And the third group is tropical cyclone moving towards the resultant of these 2 vectors. Okay, so let's see what the distribution is for the for this total of 300 cases. So actually, so we can classify for each of these groups in this 5. Actually, the 3 groups that I just showed you: the steering control, diabetic heating control, resultant control. But there are also some cases which we cannot clearly identify. So one we call it unresolvable, and one is unexplainable. We can't explain it. So that may be because the data problems and so on. So if you focus on the, and then we look at break the cases up into strong steering, where the steering flow is greater than 10 knots, normal steering 5 to 10 knots, and weak steering. So if you look at the strong steering, then the diabetic heating contribution is very small. The percentage of cases is relatively very small. So for strong steering condition, the steering control is the number of cases due to strong steering is about 5% here, but the resulting control is about 15%. So even in the case of a strong steering, the diabetic heating can have some contribution. In the normal steering, you also have this one here. The resultant control can also be, so it's a resultant control means that the combination of diabetic heating plus steering still is the largest. However, in the case of a weak steering, that the number of the percentage of total cases between the diabetic heating and the resultant is about the same. So what does that mean? That means that in the case of weak steering, either the diabetic heating control is more important, or the resultant is more important. So what this, and of course the total, you can see that the resultant is the most important control. So what these 4 panels show is that when you have a normal to weak steering, then the direction of the motion is, generally speaking, is a combination of the steering plus the diabetic heating. However, if you have a very weak steering flow, as in this case in here, then there is a chance, or a very good chance, that the diabetic heating actually could dominate the steering, because the steering is weak. So therefore, that diabetic control can dominate over the steering and contribute towards the motion of the storm. Okay, so sometimes when you are looking at, so that's probably why in the previous, many of the previous studies, that in some cases you cannot explain the motion simply by the steering, even including the beta effect. All right, so let me give some more examples in here. So this is Typhoon Rex in 1998. So you can see that the typhoon is meandering like this. And let's focus on this period here. And the reason for this is because at this time, there is a sudden southeastward movement of the storm. Okay, so there's a meandering here, but suddenly there is a southeastward movement of the storm. So if you calculate if you estimate using the Wu and Wang method to estimate the steering vector and the diabetic heating vector and compare that with the black one, which is the tropical cyclone motion vector. So this is the time. So 1998, August 2800 UTC, and so on. So what you see here is that in the beginning, also what's plotted in here is the diabetic heating term. Okay. So what you see here is that, so that's why the green vector points towards the gradient of the diabetic heating. Now, in the beginning, the steering flow is like this, and they are very close to that of the motion. Although there is a bit of contribution from the diabetic heating. So in the beginning, it's like this, and you can go back to this part here, that during this time, the motion is towards the north, and so it's mainly contributed by the steering in here, okay? However, by this time here, by the 12 UTC on the 30th, then the tropical cyclone has moved more towards the east, and although the steering hasn't changed, so the steering vector is about the same all the time, okay? But now the heating, the diabetic heating becomes much stronger, and so by the 31st 12 UTC, the diabetic heating vector is actually in line with that of the motion vector. And if you recall, 31 12 UTC is right here. Okay, so in other words, if you have a very strong heating in here, producing a very strong gradient of the diabetic heating, then it is possible that the tropical storm would not move, will not follow the steering, but instead it's actually following the heating maximum, because at that time you have a very strong increase in the diabetic heating term, causing a very strong increase in the potential vorticity tendency, and therefore the tropical cyclone will adjust towards the maximum potential vorticity tendency and move towards the area where you have the maximum diabetic heating term.
Excuse me.
Yeah. Yes.
Is this figure showing the color contour at one level or vertical average?
This is the average. So I think this is at 500. I can't remember now. Sorry. It is okay. In the mid-troposphere. It might be average over a layer, maybe from about 600 to 400, if I remember right.
Okay, I see. Thank you.
The heating is within a layer. Yes, you're right. Sorry.
Okay, so I have another question. So what is the definition of steering vector here? Do you mean the large scale flow or simply horizontal advection?
The steering vector is the horizontal advection term, the HA term.
Okay, so it may include the small scale features.
Yes.
Okay, thank you.
Yes. So it's the total HA term. So in fact, if you look at the flow pattern, you will see that the large scale flow is like this. So if you were a forecaster, if you see a flow pattern like this, then you will likely say that the storm will be moving somewhere like this because it's steered by the trough, right? However, if you look at the heating, to answer your question, Tsujino-san, it is at 500. The heating.
Okay, so at one level.
Yes.
Okay, thank you.
Yes. The heating is at one level, but if you look at the convection, this is the I think this is the heating. The shading is the IR the cloud top temperature, I think. So this shows the maximum heating is over here, and this is the maximum. This is the contours indicates the contour plot of the diabetic heating. So you have a maximum heating in this direction, the maximum gradient of the heating in this direction. And so the tropical cyclone actually in 12 hours time moves towards that direction. So that's one example in which the heating plays an important part in changing the direction of the tropical cyclone. And in fact, 12 hours later, you can see a very large, huge area of convection in here. So this one, it's at 3100. And now in 12 hours time, the tropical cyclone is now moving in this direction. Although the flow, the tropical cyclone is still embedded in the trough, and which you would expect the storm to be moving in that direction. But in fact, there's a southeastward movement. And we think it's because of the maximum heating in here that causes a very strong diabetic heating term towards in this direction, causing the storm to move in this direction. Now, another example is to look at the change in the different terms in the vorticity equation. So here is a recurving cyclone in 1990, Typhoon Flow in 1990 that actually hit Japan later on. But we want to focus on this recurvature point. So this is from 16 and 18 UTC to 17, 18 UTC. So let's look at the different terms in the potential vorticity equation, okay? So remember, we say that the horizontal advection can be broken into two terms, the advection of asymmetric advection of symmetric PV. This is the symmetric advection of asymmetric PV. And this is the diabetic heating term, so this is the total. Now, before the recurvature at this point, these two terms are very small, okay? The contour levels are the same. Contour intervals are the same. So you see the maximum at this time, at the black arrow indicates the direction of the storm. So the if you add these three terms, the distribution of the PV tendency is like this, and the tropical cyclone is moving in this direction. So, and this PV tendency is mostly contributed by the asymmetric advection of symmetric PV. Okay, so that's basically the steering. Now, however, something really dramatic changes in at this time, at the recurvature point. At the recurvature point, you can see now that the asymmetric advection of symmetric PV actually has a maximum here to the right. Now, remember in the beginning of this lecture, I show you that when you look at the vorticity change, right? That before the tropical cyclone makes a right turn or a left turn, the vorticity actually has already increased. So for example, in the case of recurvature, the vorticity has already increased to the right of the storm so that the tropical cyclone will move towards the change in the vorticity. So very similarly here, you can see that at the recurvature point, so at that time, the tropical cyclone is still moving in this direction. So but the advection, asymmetric advection of symmetric PV has already changed its distribution so that you have the maximum in here. And at the same time, the symmetric advection of asymmetric PV also became very large, okay? So if you add these two together, and heating at that time is still very small. So if you add these two together, the change in the potential vorticity is like this. And so now the maximum is actually somewhere over here, although the storm is still moving towards the northwest. Now, after the recurvature, now this is the time just right after recurvature. So what you see here, again, diabetic heating term in this case is not important. So what you see in here is now that both of these two terms are contributing significantly towards the total PV tendency, so that now the tropical cyclone is now moving towards in this direction, which is contributed by the sum of the asymmetric advection plus the symmetric advection of asymmetric vorticity. Okay, so what this example illustrates is, again, very similar to what we talk about in the looking at the vorticity tendency, that the potential vorticity tendency will change before the distribution will change before the tropical cyclone turns. And you can therefore look at the potential vorticity tendency to see where the storm will be going in the next 12 hours. Okay, so this is another example of saying that the potential vorticity tendency can be used as an explanation for why the tropical cyclone makes a turn. All right, so to summarize then, is that a tropical cyclone will move towards an area of maximum potential vorticity, which is contributed by both the horizontal advection and vertical advection, as well as diabetic heating, which is associated with convection of the tropical cyclone. So just that means if you think of it in the three-dimensional sense, then you can always think of the movement of a tropical cyclone as the change in the potential vorticity tendency, which is contributed by the horizontal advection, vertical advection, as well as the diabetic heating associated with the tropical cyclone. So that will be an extension of the Biotropic concept, which is the advection of vorticity contributed by the steering flow plus the beta effect. Okay, I think this is the last slide. So what I would like to conclude is that in the first lecture that we have, I hope I have presented a picture as to how we can understand tropical cyclone motion from both the biotropic and the bioclinic perspective. Right, so I'll stop here and see if there are any questions.
Okay, thank you very much. Any question or comment? Please feel to ask questions. You can
ask in Japanese, so Ito-san will translate.
Help translate. So. Okay, if not, maybe you can go ahead.
Okay, all right. So this concludes my first lecture on the fundamental concepts. So what I'd like to do in the rest of today and then tomorrow, the first part of tomorrow, is to talk about how we can use the concept to understand these concepts that I just presented, to understand the different types of motion that we observe in of tropical cyclones. Okay, so let me stop share this one first, and I'll share another PowerPoint. Okay, now the rest of today and then the first part of tomorrow, I will try to use these concepts to explain some of the observed motion of tropical cyclones. So for this part, I will talk about two things. One is on binary interaction. And again, I will start from a simple concept of biotropic, using the concept of biotropic vorticity, and then how that might be modified if we include the bioclinic processes. And then the second example I want to show, or a second application I want to show, is how recurvature can be applied or explained from the beta effect. Okay, so the first is binary interaction. So let me give you an example, a study that was when I was a forecaster in the Hong Kong Observatory. So 1986, when many of you were not born, there were two storms, one in the South China Sea. So these numbers indicate the dates, okay? So one in the South China Sea, let me use the pointer again. So on the 18th, there were two storms. One is in the South China Sea, and one is over the Pacific Ocean in here. And then I was a forecaster here. There's Hong Kong here. So we saw this storm and said, oh, we're going to have to issue warnings for the tropical cyclone. And if you look at follow the track, then it's likely to hit Hong Kong. So we were worried. But then it just suddenly turned just to the south of Hong Kong and then move and go over Taiwan. And he said, okay, well, great. We don't need to worry about it anymore. Then suddenly it turned back again on the 25th. And they said, we worry again, it will hit. But then it turned again the second time. So the 22nd, 27th, 28th, and then the third time, it came back again. And then, but finally it made landfall in Vietnam, okay? So it's a very, it caused a lot of headache and large forecast errors, obviously. But it turns out that the reason why you have such a strange track is that there was another tropical cyclone Vera. So this is tropical cyclone Wayne, and this one is tropical cyclone Vera. There was another storm that made similar strange tracks. Okay, so it's 18th, 19th, 20th, and on the 22nd, it made a 180-degree turn like this, and then finally hit Korea on the 28th, and so on. So what's going on in here? And what we found was that if you plot the center of Vera in here, and then plot the track of Wayne relative to the center of Vera, you see that the track goes around like this. So there was a period when the tropical cyclone Wayne was rotating around, so it's almost at the same radius, around the tropical cyclone Vera. So Vera was doing its own thing, but then Wayne was actually rotating around Vera, right? So that was a very memorable case for myself. So that's why I wanted to show you first. Now, of course, there are many of these cases that we have seen, and some of you, if you are a forecaster, you probably have seen this as well. So this is in 2006, and Mark Lander gave this plot to me, and so I thought that was very good. So I used it. And so what you see here is that at some point, Sao Mai in here and Bopa, they kind of approach each other. So we call this the approach. And then they start to capture each other like this. And then they start to orbit. And at some point in here, Bopa actually dissipated and Sao Mai continued its own journey. So you have this very typical approach, capture, orbit, and so on. And the distance between the two is about 600 nautical miles. Okay. Now, of course, this happened many years ago. Also, in fact, it happened quite often in the Western North Pacific. So this was a plot many years ago by Dong and Newman in 1983. They looked at the case of Marie and Kathy, that they actually came together and they rotate around each other. So very nice rotation in here. So Kathy rotates like this and Marie rotates in the same way. So you can see that you have this rotation as we move along, okay? Now, even before then, there was a study by Sam Brand in 1970 that he looked at two storms, so storm 1 and storm 2, and look at the angle change between the two storms. Okay, so this is 000612. So then he calculated the angular change in here. So he plotted the angular change in the x-axis and the separation distance in the y-axis. Okay, so 0 means there is no angular change. The two storms just move on its own. But what's interesting is that as you go to shorter distance, separation distance, so if you have over here about 800 nautical miles, there's not much change. But then as you go towards shorter distance between the separation distance between the two, you can see that this rotation, the angle becomes larger. So that means as the two vortices get closer to each other, then they start to rotate a lot more, right? So there's a large rotation in here. But there's also something that you can notice in here. There are some cases in which the actually, sorry, this scale is wrong. It should be nautical miles. But in any case, you can see in here that there are some cases in which the angle is negative. What does that mean? Negative means that there is actually a clockwise rotation, because this is counterclockwise, right? This is counterclockwise rotation. So therefore, there are actually some cases in which the rotation was clockwise instead of counterclockwise. So that's interesting. We'll come back to this in later on. Okay. So while in most cases there is this counterclockwise rotation, in some cases there's actually this clockwise rotation. Okay. Now, so actually Dong and Newman look at how many cases there are in terms of counterclockwise and clockwise. And there are some also cases in which there's called indeterminate. So this is the percentage frequency versus the distance. So this is the number of separation distance units. So that's basically the distance in terms of degrees latitude. So this is 2 to 4 degrees, 4 to 6, and so on. Okay, so if the two are very close to each other, you can see that most of the rotation, the highest percentage. So of course, when they are very close together, they are very number of cases is very small, simply because they're too close, right? So they might just merge already. So the number of cases is very small. But so focus on these few cases, few columns in here. So 4 to 6, 6 to 8, 8 to 10, and so on. So there are more cases in these categories. And what you see in here is that in these 4 categories, 4 to 6 to about 10 degrees, then the percentage frequency is the highest with a counterclockwise rotation. Okay, so you can see that you have a highest percentage is counterclockwise rotation. This is a few cases of clockwise rotation. Now, however, if you go to larger distances, then the number of cases or the percentage of frequency of the counterclockwise rotation versus clockwise rotation is about the same. So therefore, if they are further apart, then they could have a chance of rotating in the opposite direction. Okay. So Mark Lander drew this picture in 1995 and showing the different possibilities of this binary interaction. And so it started out with 2 storms making an approach like this. And then at some point there's a capture. So the 2 storms capture each other. And then they start orbiting each other, as shown in here, that they orbit each other. And then at some point, they could either merge like this, or they could escape. Okay, so therefore you could have this is the kind of a schematic diagram of the type of interaction that you have. You have approach, capture, orbit, and then they would either merge or they would move apart from each other, escape. Okay. So the concept, so this is the observations that when you have two storms that are close to each other, then there's a possibility that they interact. So of course, we all have heard of this. It's called the Fujiwara effect, which was discovered by Fujiwara in 1931 from laboratory experiments. But in the real hemisphere, that's what we saw from different types of studies based on observations. So what we'd like to do is understand a bit of why this rotation occurs. Okay. Now, Mark DeMaria and myself did a study, a numerical study in 1984. If you have two vortices, this is the tangential wind distribution, and one is a small vortex like this, B equals 1.0, and the dashed line is a big vortex where B is equal to 0.5, okay? Now, if you look at the track of these two, if you put two vortices like this, that are about 600 kilometers from each other, like this, then the small vortex, the solid line in here, there's no interaction. They just move away from each other. However, if they are these two bigger vortices, then they start moving towards each other, and then they finally merge. Okay, so the question is, why do we have when you have the same distance, all right? Both vortices are at the same distance from each other, but one is a small vortex and one is a large vortex. A small vortex just move away from each other, but the large vortex move towards each other. So what is the reason for this? And we think the reason is because in a large vortex, in a small vortex, first of all, in a small vortex, the vorticity distribution is like this. So there's a change in the vorticity gradient. So this is a decrease, but then there's actually an increase in the vorticity, like this. Okay, the vorticity gradient changes. However, for the bigger vortex, the vorticity gradient simply decreases as a function of distance. And recall that this is the, remember, we think that in the Biotropic case, that it is the invection of relative vorticity that determines the movement of the tropical cyclone. So if you look at the movement of the, so later on we extended a bit of the study, and to understand a bit more, then we did the same thing with, now we did three vortices. The big vortex is 0.5, the small vortex is 0.1, and the middle one is 0.7. So you can see again that if you have a 1.0, then again the vortex don't interact with each other. When you have a B equals 0.7, then it starts to rotate about each other. And then when it's B equals 0.5, really big vortex, the solid line in here, then it starts to rotate like this. Okay, so why do we have this difference? And the difference, as I mentioned, is because of the vorticity gradient. Now, so if you just compare the two vortices, the two experiments, one is B equals 1.0. This is the small vortex. This is the big vortex. So in the small vortex, this is plotted the relative vorticity distribution. So what you see here is that of course this you have a maximum vorticity in here in the center. Then on the outside, there's a decrease in the vorticity, obviously, but in the middle, there's actually a change in the vorticity gradient. However, in the big vortex, the two vorticity distributions actually merge with each other. So the whole distribution of vorticity is like this. There's no change of the gradient in the middle. Okay. So as a result of that, after 12 hours of integration, And if you look at only the asymmetric flow, that means you subtract the symmetric part of the vortex. You see that for the small vortex, the flow is like this. So this is for the left vortex, okay? So both cases is for the left vortex. And on the left-hand side is the small vortex, and on the right-hand side is the big vortex. So what you see here is that the asymmetric flow for the small vortex is actually like this. Whereas for the big vortex, the flow is like this. So because you have a bigger vortex, the tangential wind goes much farther, and therefore it extends to the other vortex, and therefore you will have this different in terms of the flow. So if you want to understand a bit more, again, using Fiorino and Ellsbury's methodology to break the flow into the three components: asymmetric advection of symmetric vorticity, symmetric advection of asymmetric vorticity, and the asymmetric advection of symmetric vorticity, you can then calculate the different terms. Okay, so the first column is the symmetric advection, the second column is the asymmetric advection, and then this is the local change in the vorticity. So what you see here is that in the small vortex, from the symmetric advection of asymmetric vorticity, you actually produce a, again, this is for the left vortex, you produce a positive and negative in here. And then the asymmetric advection actually produces a positive in here, okay? However, if you add these two together, then you will see that the maximum change in the local, maximum change in the vorticity is now to the southwest of the storm. So the black dot is the center of the storm. And whereas in the big vortex, the distribution of the symmetric advection of asymmetric vorticity is very different from this one here. And that's because the vorticity gradient is different. And so the advection, the symmetric advection of asymmetric vorticity becomes very different. So therefore, if you add to the asymmetric advection of symmetric vorticity, then you will get a distribution like this. And because of that, in the case of a small vortex, the storm will be moving towards the southwest, whereas in the case of the big vortex, the storm will be moving towards the southeast. And as a result, the bigger vortex will have a rotation towards the other vortex, whereas the small vortex will have a rotation that's pulling the storm apart. So in other words, you cannot just explain by the advection itself, by the asymmetric advection of symmetric vorticity itself. You also need to look at the symmetric advection of asymmetric vorticity because of, and the reason why there's a difference is because what you see in here, because of the distribution of the vorticity with a different gradient in here compared with that over here. Okay.
So Johnny,
right.
I have one question. So if my understanding is correct, the approach of two vortex is coming from the vortex-vortex interaction.
Yes.
Kind of. So here, if we do not have a negative vorticity outside, they do not come closer to each other, I think. I'm sorry, they do not go apart.
If there is no negative vorticity, yes.
Right. So just, I think in this case, the negative vorticity, existence of negative vorticity also contributes to the large difference between these two, types. Is that correct understanding?
Yes. It's exactly because of the negative vorticity for a small vortex that contributes towards the moving apart of the two vortices. Yes.
Right.
Yeah.
Okay. Thank you.
Okay, but it's that there's another interesting part about this interaction. So if you now run the model on a beta plane, so this study here is on an F plane. Okay, so beta is equal to 0. So there's no beta effect in here. It's simply because the interaction of the two vortices. But if you go a step further, and now you include the beta plane, so you run the model on a beta plane, you have a very interesting result. So this is the case where B equals 0.7. So therefore you have this rotation in the red. Okay, so if beta equals 0, you have a very nice rotation in here, like this, as you would expect, as I said before. But what's interesting is that if you now include beta, so the green indicates there's the beta effect in here, then the cyclone actually rotates like this. The right vortex moves like this, and the left vortex moves from here, goes up like this, and rotates like that. Okay? So why do we have this? And that's actually because the whole system, these two vortices, can be considered as a big vortex. And because if you look at the center of mass between the two systems, and you follow the center of mass, it actually moves towards the northwest. So in other words, what you can think of is like this. So you have two vortices, right? So they rotate about each other like this. But at the same time, you can think of the two vortices together as a huge, large vortex that moves towards the northwest under the beta effect. Okay? So while they interact with each other, the whole system moves towards the northwest. Right? So that's important. So therefore, when you start looking at in the real atmosphere, when you look at the interaction between the two vortices, you cannot simply look at the rotation. So of course you can look at the rotation relative to each other, but if you look at the center of the mass, they're actually moving towards each other, moving towards the northwest. Because if you subtract the motion relative to the center of mass, you actually get almost exactly the same. So that proves that the track that you see in here, the green tracks in here, is because the center of mass is moving. And therefore, if you plot the position relative to the center of mass, then the two will be exactly the same. Okay? So that's a very interesting result. Again, if you put in a background flow, then you get a bit more complicated. So if you put in a background flow, beta is not equal to 0, then the rotation now becomes a bit more complicated. So the cross simulations when you have an anticyclonic shear, the dashed line is when you have a cyclonic shear, and the solid line is when you have no shear. Okay, so you can think of it like this: when you have a cyclonic shear, your entire system behaves like a very large vortex. When you have an anticyclonic shear, that the vortex actually becomes smaller, right? And again, if you plot the center of mass, you will actually see something like this, that a cyclonic shear will be like this, and an anticyclonic shear is like this. It's kind of like what we talked about, the different size vortices. The bigger vortex, that means when you have a cyclonic shear is when you have a huge vortex, right? So remember in Fiorino and Ellsbury's study is that when you have a big vortex, it tends to move faster and more to the west. And this is exactly what you see in here. Whereas in an anticyclonic flow, that means the vortex, the net vortex becomes smaller, and so therefore it moves more towards the north. So that's consistent with the study for one vortex in the Fiorino and Ellsbury case. So therefore, the summary is that the binary interaction depends on the relative vorticity distribution of the two vortices, as we said. And then the two vortices interact with each other. But very importantly is that the binary system moves as a large cyclonic vortex moving towards the northwest, in the northern hemisphere under the beta effect. And a background shear flow, whether it's cyclonic or anticyclonic, can modify the relative track of the two vortices. Okay, so in the real forecast of tropical cyclone binary interaction, we need to take these 2 points into account. Okay, we need to think about this as we do the forecast. Right. So
excuse me.
Let me stop here.
Can I ask a question?
Yes, please.
So if the separation distance between two vortices are larger, so do the two vortices, I guess the two vortices do not act as a one vortex. I mean,
yes,
right.
That's
so
right.
In that case, the center of mass does not move toward the northwestward.
Yes, if the two, so if you go back to this one here, so if these two vortices do not rotate about each other, then there's no sense. Then they I mean, if they move apart, of course, I think in that case I think we've done a study on this, and there's no movement towards the northwest. But I'm not. I need to go back and check. My recollection is like this, but this was done many years ago, so I need to go back and check. But I think if the two vortices don't interact with each other, then the whole system probably does not move towards the northwest, I think.
Okay, thank you.
Other questions?
Okay, if not, you can.
Okay, all right. Now let me spend a few minutes talking about the baroclinic concepts. And this is so again, when you think about the three-dimensional atmosphere, you need to think about the baroclinic concepts. And this is a study done by Ito-san and Professor Lee from Korea and myself, looking at the simulation of different vortices in a baroclinic atmosphere. So we did quite a number of experiments, and the labels are like this. So we did different separation distance, as in D, and there's different radius of maximum wind. So that kind of relates to the size of the storm, and also the I for different intensity. So if you look at the set of vortices in here, so the red is the left vortex and the blue is the right vortex, and 0, is the center of mass of the two, and these are identical vortices. Okay, so this will be a separation distance of, so this first one here is 600 kilometers, and so the separation distance 600 kilometers, 800, 1000, and so on. Okay, so all the way up to 1600 kilometers from each other, like that. So what you see here is very interesting, is that when the storms were 600 kilometers apart, then they rotate about each other. So you have the red vortex rotating like this, and then the blue vortex rotate, and they eventually merge into here. For the 800, so D08, I said these are all identical vortices. So the only difference between the different experiments is that separation distance. So you see in the D08 that the two vortices still rotate about each other, but during the time of our integration, they haven't merged, but they rotate about each other. But as the separation goes further to 10, that means 1,000 kilometers, then they start to separate like this. Okay, so they start to separate like this, and the further you go, the more separation you can see in here. So in fact, as you go further out, that the rotation, if you think that there's a separation, it's actually in the clockwise rotation about each other. Right? Now, what about if the vortices are not identical? So because this D08 case is when it starts to rotate, so we choose to move to run experiments with D8 the separation distance of 0.8, but with different intensity, different radius of maximum wind and different intensity. So here is the case, the two runs, one with higher intensity. So in here, you have an experiment when you have the intensity of 60 meters per second for the right vortex, but for the left vortex is 60 meters per second, but for the right vortex is still 30 meters per second. So what you see here is that for the high intensity, the rotation of the left vortex becomes more. So it rotates, the right vortex doesn't change very much. It rotates a little bit more, but it's not as significant as the left vortex. So the high intensity means that you have a stronger interaction between the two vortices. But more importantly is that when you have a larger vortex, so larger vortex means that on the left vortex has a radius of 600 kilometers, but the right vortex is still the same with the 300 kilometers. So in that case, the right vortex was swung. It swung a lot more like this, right? Whereas the right vortex, the left vortex, it still swings a bit more, but the effect is huge for the right vortex like that, right? Now, if you combine the two with a very high intensity in a large vortex, then the left vortex is like this, which is similar to this one here, and the and the left vortex again was swung like this. So what it means is that the size of the vortex actually has a larger effect on the interaction than the intensity. There is some effect on the intensity, as you can see in here, but the change is not as large as that for a large size storm. So why is this the case? So let's look at the case for the identical vortex first. And again, we would use the potential vorticity tendency perspective. That means calculating the different vectors. So this is the horizontal advection vector, vertical advection vector, the diabetic heating vector. We also look at the friction. And the black is the tropical cyclone motion vector. So what you see here is that at 500, and what we plotted here is the potential vorticity tendency. So first of all, you can see that the potential vorticity tendency is where the tropical cyclone is moving. So this on the left column is the case where you have the separation distance is 600 kilometers, and on the right column the separation distance is 1,000 kilometers. So here, what you see is that the when you have at 500, the contribution for this case is that you have the contribution from both the steering, the horizontal advection, and the diabetic heating. The combination of these two then causes the tropical cyclone to move in this direction. However, in the case when the two vortices are separating, then the heating, the vertical advection and the heating is very small, and mostly is contributed by the HA term. And at 300, there's a bit different, but nevertheless, you can still see that so of course at 300, the heating becomes a bit more significant. But if you combine the three vectors, you can still see that the motion of the vector is a combination of these three vectors. So the conclusion here is that you can actually explain the motion by a combination of the horizontal advection and the heating. Now, so the heating, therefore, in some cases can contribute significantly to the motion of the storm. Okay, so why do we have this heating and it's this change in the heating? And if you look at the vertical wind shear, you will see that in the case when you have when the two vortices are very close to each other, the shear has a different distribution than that in the case when the two vortices separate. So in the case when the two vortices separate, you can see the shear distribution is elongated in the northeast-southwest direction, so that the shear vector will be different compared with the case when you have the two vortices that are close to each other, in which you can see that the shear is quite symmetric, and that leads to a different heating distribution. Now, to understand a bit more of that, we did an experiment when there is no heating to see the contribution of the heating. So in the case of in this case, so this one here is when you have it's the previous experiment, and this one is when you have no heating. So what you see here is that when there is no heating, then the vortex simply rotates about each other and merge, right? Now, remember we say that when there is no heating, you can basically consider that as like a biotropic situation. When the two vortices interact with each other, then they can merge. However, when you have the heating, then the vertical shear then causes the diabetic heating to change, and therefore the movement of the vortices becomes different. So in other words, when you have in a baroclinic atmosphere, when you have the two vortices put together, a very important factor arises that is not present in the barotropic case, which is the vertical wind shear, because the two vortices, when their two circulations are overlapping each other, then it forms a different types of, so it produces a vertical wind shear. Now, when you produce a vertical wind shear, all the studies previously show that when you have a vertical wind shear like this, the convection, the maximum convection in general is down shear to the left of the vertical wind shear vector. So therefore, you will now create an asymmetric convection down shear to the left of the shear vector. And as a result of that, it changes the diabetic heating distribution, changes the potential vorticity tendency, and therefore changes the motion of the storm. Okay, so schematically, you can explain the motion of the binary action due to vertical wind shear is that the low level and the cyclonic, low level cyclonic, upper level anticyclonic circulations like this will produce a shear in this direction, so that you would then develop a shear-induced asymmetric heating, which then modifies the track. So in both cases, you have the asymmetric convection, which then modifies the track of the tropical cyclone. There's a question here. No. Oh, okay. So the summarize is that the binary interaction can be modified by the vertical wind shear generated by the upper level flow associated with the anticyclonic circulation of the two vortices. That's very important. So the asymmetric convection due to the vertical wind shear then modifies the diabetic heating term in the potential vorticity tendency, and therefore changes the track of the two vortices. So in other words, if you only study, if you look at binary interaction simply as a result of the vorticity distribution, then you ignore a very important term, which is the vertical wind shear that's not present in the biotropic concept. So I think that's the end. And so therefore, binary interaction cannot be completely explained by the biotropic concepts. Okay, so that's about the binary interaction. So see if there are any questions before I move to the second part of the application. Any questions?
Any questions or comments?
I have one question, okay?
Okay.
Yes.
I'm
Please.
wondering if your concept is consistent with observation. So I'm wondering, can you check the real atmosphere situation?
You mean when you look at the baroclinic concepts with
yes,
with
yes.
heating? Okay, that's something that we're working on right now. In fact, I think Ito-san might give some comments on that one.
Okay. So yeah, I investigated those features recently, and I found that actually the direction of vertical wind shear and also the asymmetric diabetic heating occurred as expected in this idealized simulation. And however, the cases are very complex, and in some cases, vertical wind shear directs to this direction, sometimes this direction, but overall, the diabetic heating, I just made sure that the diabetic heating at least serves to not separate. Tropical cyclones tries to get closer to each other without vertical wind shear, but vertical wind shear tries to stop to getting close to each other. So binary interaction, I just made sure that binary interactions are not very good separation by diabetic heating, but at least I made sure that diabetic heating is another important source to change the tropical cyclone motion when two tropical cyclones get closer to each other. Yeah, I will show in the next some conferences.
Okay, thank you.
So conceptually, this should be the case, right? So, I mean, we always think of the motion as the combination of the invection and the diabetic heating. So conceptually, we all know that when you have the two vortices that are close to each other, so for each vortex, you would have the anticyclonic circulation. So that when the two anticyclonic circulation are close to each other, then they would then modify the anticyclonic circulation, which therefore would change the vertical wind shear. And if you change the vertical wind shear, then we all know that it will affect the distribution of convection. And if you have this change in the distribution of convection, then you should change the diabetic heating distribution. And therefore, you should change the potential vorticity. So, but of course, like Ito-san was saying, is that in the real atmosphere, there are many processes. So we need to pick some cases, like in the case what I showed you before, on looking at for example, the case of Typhoon Rex. We happen to find this case where you have a sudden change in the direction of motion, and we found that there was this huge area of convection. So in the case of binary interaction, we will still need to do something like this. But of course, as you know, that binary interaction occurs maybe once or twice a year, or sometimes there's no case per year to look at this. So to find cases like that may be not easy.
So one thing I can say is on a composite basis, the vertical wind shear contribution to the TC motion is about 1 meter per second of translation speed or more.
I see.
Yeah.
Thank you.
So it may not be the very dominant term, but I think it must have some contribution.
Okay, thank you.
I have a question to Ito-san. So, did you check the diabetic heating in reanalysis data?
Reanalysis data, yes.
Okay, thank you.
Any other question or comment? Okay, so 30-40 minutes left for today.
Yeah, I will just, this one is not going to take too long. This is a very interesting study that I want to show related to the beta effect. And so quite a few years ago, we did a very interesting study. This is on the beta plane, so it's all baroclinic, no background flow, and we put 3 vortices at the same longitude. Okay, so here, here, and here, one at 25 degrees, one at 30, one at 35. And we just ran the model for 72 hours. So what's interesting is that the vortex at 25 degrees latitude will just move towards the northwest as what you would expect under the beta effect that you have like this. However, if the vortex at 30 degrees still move towards the northwest, but it's more towards the north. And very interestingly, when you put a vortex at 35 degrees north, it actually recurves like this. All right, so it seems that as a tropical cyclone, so a tropical cyclone under the beta effect can actually cause itself to recurve if it is at a very high latitude, as in this case. So the question is, why do we have this type of result? So because it's so we now, instead of looking at the convection, we look at the vertical wind shear. We look at the vertical wind shear, the winds average over in the lower troposphere, mid troposphere, and upper troposphere for the and for the 25 degree, 30 degrees, and 35 degree vortices. So what you see here is that if you integrate for 6 days, then the vertical wind shear in the lower, in the low latitude case, is that there's the vertical wind shear is like this. But if you compare that with the 35 degrees, then the vertical wind shear is much larger. Okay, there's no background. So therefore, it's not because you have the westerlies. Okay, there's no background. It's just simply the flow generated by the vortex itself. So the reason for this is because the upper level flow becomes much stronger. Because if you look at the low level flow, it's quite similar, right? So there's not much different. And the mid-tropospheric flow, generally speaking, is very small. So the reason why you have a strong vertical wind shear in here is because the upper level flow is very strong. So why do we have this? And it looks like that if you look at the at 25 degrees latitude, the vortex, so this is at 200 hectopascals. Sorry, is it two? Maybe it's 200. So of course you have the cyclonic flow in the center of the vortex, and then it goes out like this, right? So that's typical. But what's interesting is that at the level at 25 degrees latitude, the anticyclonic flow is to the southwest of the storm. And it generates the anticyclonic flow like this. But at latitude 35, the anticyclonic flow is generated in a different location. Okay, so you can see that the anticyclonic flow, instead of like that, it's actually to the east, and it rotates much slower than that of the case of latitude 25. So as a result of that, if you look at the shear in here, you can see the winds. So the shading is the wind speed. So you can see that the shear, if you average around here, that the shear in here is much stronger than the shear in there, right? So we think that because of the shear, it causes the vortex to have so if you go back to this, so because of the shear is being much stronger, then you will have a down shear left connection, and that is what's causing the storm to move differently. Okay, so if you have a very strong shear in here, so the storm will tend to move in that direction, whereas because the shear is in a different direction, then the convection is in a different direction. So therefore, it doesn't. The contribution of the heating is not causing the vortex to move to do the recurvature. So, sorry, wrong direction. So we actually look at one example. Here's a storm that's in the core region. So the steering flow is very weak, but it still recurves. Even though the storm is only at 30 degrees, but it still recurves like this. So if you look at the shear, we found that there is a strong development of the vertical wind shear, very similar to the model that we have. And as a result of that, this shear then causes a convection to the down shear left, and therefore it actually causes the vortex to recurve. So this is only one case, and we're still doing more studies as to whether this is true, that a vortex is going to recurve under its own because of the beta effect causes the wind shear to be different, and therefore the track to be different. So I'm just showing this as hopefully somebody will try to think about a little bit more about this. So the differential beta effect in the vertical actually modifies the upper tropospheric flow and change the horizontal evection, potential vorticity, and vertical wind shear, and therefore the distribution of convection. And so the tropical cyclone can actually recurve in the absence of an environmental steering flow. Okay, so this is a very preliminary study that we did to see when you have in a real atmosphere, the contribution of vertical wind shear is actually important. Not only in terms of, we all talk about vertical wind shear in terms of changing the intensity of the storm, but what we have seen in some of the studies I presented today is that the vertical wind shear can change the distribution of convection and therefore changes the track of a tropical cyclone. Okay, so it's a bit early, but I think I will stop here for today. So let's have some general discussion before we close. Yeah.
Okay, so I'm sorry. So I was wrong for the time. You know, actually, the 5:30 is the time to end.
Oh yeah. That's right. So we are right on time.
Yeah. Okay. Good. So for the last topic is very very interesting. So anyone have a question?
So may I ask a question?
Yes,
Sure.
please.
So I couldn't understand why the upper tropospheric flow is generated in this case. So can you please explain that again?
Well, there is always a. So this is a three-dimensional simulation, right? So therefore, the upper level will have an anticyclonic circulation.
Yes.
So this anticyclonic flow is simply because for in the upper troposphere, when you have the outflow, it will generate this anticyclonic circulation.
Yes.
But but the anticyclonic circulation is different when at different latitudes because of the beta effect.
So that's why the eastward upper tropospheric flow is generated.
Yes.
So another question is, did you calculate the contribution of diabetic heating in this case? In the PBTNC equation?
Yeah, we have not done a detailed calculation of this. So as I said, this is a very preliminary study. So we will try to do a little bit more on understanding about the different contributions of the diabetic heating versus the horizontal evection.
Okay, thank you.
Yeah.
So I talked with the Kelvin Chan, who is the first author of this work about the topic, and if I understand correctly, I think this can be understood as a reversed beta gyre in the upper troposphere. Is that correct?
Yes.
So
yes.
in a lower level, we have the from southeast to northwest, kind of two gyres, and in upper troposphere, the opposite thing can happen, and that was my basic understanding. So that's why kind of the gyres can happen. So, other questions or comments?
I have a question.
Okay, sure.
If you continue the integration beyond the 7 days, would you expect the cyclone in the high latitude case to proceed eastward, or would it recurve to southward and circle clockwise?
That's a very good question. We only stop at 6 days, so maybe we should do a bit more to 10 days and see what happens. We didn't do it. No, we stop at 6 days. Yeah.
Oh, thank you.
Sorry.
Okay, any other one more question? Okay, so if not, today's session is ended. So just big applause to the Johnny Chan for the first day's talk.
Thank you.
Okay, so I'd like to say something. And at first, we want to take a picture, group photo. So if you can show up, please show your faces, and I will take the capture of your faces. Okay, so thank you very much. So I can only take pictures of 25 persons in one shot. So I think I need to take 2 pictures. Okay, first 25 person. Okay, 1, 2, 3. Okay, thank you very much. And next shot. Okay. One, 2, 3. Okay, thank you very much. I took 2 photos of 25 persons each. And あれですね。篠田さん, so I think you already opened the dinner website, right?
Yes,
Okay.
because the town is already open. Yeah.
Okay, so, and I originally said that, we will start the dinner time from 6 o'clock, but I think some people want to go home. So I think it's, somebody can start your dinner now by joining the website, but we will toast around 6:30. How is that?
Okay.
Okay.
So you can join the dinner now, but we will toast 6:30. So
Okay.
prepare your food before that time, and if you can join, please enjoy the conversation at that time. Okay, so anything else? Shinoda-san, any other comments or anything?
Okay, no.
Okay,
Thank you, Ito-san.
Okay, so
thank you, Johnny.
So
Okay, I'll talk to you in the dinner.
Okay, so
Okay.
it's a very good chance to talk with Johnny, by one-to-one, face-to-face, kind of a face-to-face talk. So please join the dinner time and the tomorrow session. Okay, so tomorrow's session will also start at 2 o'clock p.m. in Japan and Korea, and 1 p.m. At Hong Kong time. Okay, so please come back again. Thank you very much.